Okay, so we're continuing our discussion of linear algebra from 7.3 now in the Boyce and DePrima textbook, and they put a lot of information in this section. So I just wanted to focus on two things here. The first thing is the four fundamental subspaces that are attached to a matrix, and how you can use these subspaces to determine the solution or solve AX equal B. And then the second thing we'll review is just the some nuts and bolts of eigenvectors and eigenvalues. Okay, we're going to actually look at this more in depth again later once we get out of the differential equation section, but this section here will be very useful later in the week. All right, so let's take a look first at the four fundamental subspaces. Let A be an m by n matrix. Okay, then you can visualize, or you can think of the matrix A as a mapping. X to AX is like a mapping, maybe you could call it F, where if X is in Rn, right, then AX is in Rm, and this is the case, right, where A is m by n. Good. So the domain here is n-dimensional space, and the range is m-dimensional space. And so you can break those spaces apart by a little cartoon. So I'm thinking of this first coordinate system really as the graph of Rn, and this one is the graph of Rm, although I'm just showing them in 2D. And the beautiful thing about these, this is your domain, right? This is your range. The beautiful thing about this is that you can examine the solutions in terms of these subspaces, number one. And number two is that these look like they're at right angles to each other, and in fact they are. So that means that any vector in the null space of A is going to be orthogonal to anything in the row space of A. Let me finish that up. By the way, if we were in complex numbers, this would be the null space of A star here, the adjoint of A. And so maybe we should actually define what these spaces are. So the row space of A is the set of all linear combinations of the rows of A. And in this case, we usually think of the rows as being in column form, right? We don't usually work with the rows as rows. Similarly, the column space of A is the set of all linear combinations of the columns of A. Good. Null space of A, it is the set of X such that A times X is equal to 0. Okay, so it's the set of X in Rn that gets mapped to the 0 in Rm. Alright, so similarly, the null space of A transpose, or the null space more generally of A star, would be the Y in Rm such that A star Y equals 0. Okay, now suppose I'm trying to solve AX equal B. Now before we actually go to solve this, I think it's good to remember, well, what does A times X represent? Well, A times X is actually, let's see, it's m by n, okay. It is the linear or a linear combination of the columns of A, right? A times X is a linear combination of the columns of A. Where have we seen linear combinations of the columns of A? Column space of A. Therefore, AX equal B has a solution only if B is where? In the column space of A. Otherwise it does not. Good. Now, how would we tell if AX equal B has a unique solution or not? Is there anything about the four fundamental subspaces that would tell us that AX equal B has an infinite number of solutions? And there is. And that is that if X is completely contained in the row space of A, then AX equal B has a unique solution. So what we're saying here, something equivalent to this, is we're saying that the null space of A is just the zero vector, right? Because otherwise, if the null space of A is not the zero vector, then if you have xp solving this equation, right, you could add on x sub h, right, where x sub h is in the null space, and then if you take that into A, right, you still get your b plus 0, right? So therefore, if the null space, and I think another, probably better way to say this, maybe, let's see, if the null space of A is equal to 0, then that's better to say it that way. Good. Okay. So then, let's see, how many things have we gone through? So far we've looked at when does AX equal B have a unique solution? When does AX equal B not have a unique solution? Well, if the null space of A is not just the zero vector. By the way, if A is a square matrix and it has a unique solution only if the matrix A is invertible, right? So, but A might not be square in this situation. So then we have an infinite number of solutions if the null space is more than just, is not equal to the zero vector. Good. And then finally, when do we have no solution? AX equal B has no solution if B is not contained in, not an element of, the column space of A. Well, if it's not in the column space of A, where is it? It would be over here somewhere. And so instead of solving for AX equal B, we project this to the column space to get B hat, and then we solve AX hat equals B hat. And then X hat is not a solution to the original equation. It'll be the least squares solution. I don't know if this sounds familiar to you. You don't have to know this right off the top of your head. This is more like just reminding you of some of the things that'll happen. And we're going to take a numerical example to try to illustrate these a little bit better in the next video. See you then.